this tool is provided by the operating system for user processes to solve their critical section problem. Okay, so semaphore is nothing but one integer variable, but unlike other integer variable, it cannot be operated, or say arbitrary integer arithmetic cannot be performed over semaphore variables. Only two operations defined by the operating system, that two operations can be performed over a semaphore variable, and that two operations are called p operation and v operation, or the wait operation and signal operation. P is the wait operation and V is the signal operation, right? So wait and these signal operations are atomic. So this means that either they would be performed in its entirety or they would not be performed. So in between. So while one operation is being performed, it is not likely that the currently running process would be, say, stopped and context will switch to another process until and unless the wait or signal, as we know, it is unconditional. But wait operation is conditional if it has to say wait. So this, if the value of the semaphore is less than equal to 0, then it would be stuck in the loop, right? So this implementation of the semaphore leads to some problem which we already have studied. This implementation of semaphore leads to one phenomena which is known as busy waiting. Busy waiting, say process which is waiting to acquire the semaphore. So that acquiring a semaphore means successfully decrementing the value of the semaphore. Okay, so successfully performing the wait operation. Okay, but if the value of the semaphore is greater than 0, then the process would be able to successfully decrease it, and this wait operation will be successful. But if the value of the semaphore is less than equal to 0, then the process will be stuck in a loop. So the time quanta, so if it is round robin, the amount of time that is given, so the entire time it will be wasting checking whether the value of the semaphore has become greater than 0 or not. So this is called busy waiting. So this kind of implementation, this sort of implementation of this semaphore leads to this phenomena which is called busy waiting. Okay, the process is waiting to acquire the log, but it is kept busy. Okay, যে এক্সাম্পলটা তোমাদের বলেছিলাম, তুমি রাস্তায় বা রেল স্টেশনে তুমি ট্রেনের জন্য ওয়েট করেছো, কিন্তু কন্টিনিউয়াসলি তোমাকে ট্র্যাকের দিকে তাকিয়ে থাকতে হচ্ছে, বা সিগন্যালের দিকে তাকিয়ে থাকতে হচ্ছে, বা তোমাকে অ্যানাউন্সমেন্টের জন্য কানটা খাড়া করে রাখতে হচ্ছে যে কখন ট্রেন আসবে তার ঘোষণা হবে, বা কখন ট্রেন আসবে সিগন্যালটা সবুজ হয়ে যাবে তুমি দেখতে পাবে, কারণ কন্টিনিউয়াসলি তোমাকে দেখতে হবে, না হলে তুমি ট্রেনটা মিস করে যাবে কখন চলে গেল। ওকে, তো ইউল বি কেপ্ট বিজি waiting for that event. So whether that event has occurred or not, it will be in a tight loop. So that actually wastes your time. So you could have used that time in other fruitful work. So in this case, what happens if a process has to, so this wait operation, implementation of this wait operation was actually revised, and we had this implementation of the semaphore, and we discussed it in the last class. With the semaphore we have the value. So semaphore has got two things. One is the value associated with that, integer value associated with that, and another is a list of processes associated with that semaphore. List of processes associated with that semaphore. Okay, so if a process has to wait for that semaphore value to become greater than 0, then that process need not continuously check whether the value has become greater than 1, greater than 0 or not. That process can block itself. That process can block itself and go on. Process can block itself and go to sleep. That means this process will be removed from the ready queue, so it owned the schedule, thereby saving precious processor time, which could be given to other processes who need that. Okay, So wait operation is defined as this semaphore value is decremented first. Then if the value of the semaphore has become less than 0, then this process would be added to the list waiting for that semaphore, list of waiting processes waiting for that semaphore, and that process would be blocked. So it won't be scheduled further, right? After that, so when a process which is in critical section come out of this critical section and does a signal operation, it would just increase the value of the semaphore and will check whether the value of the semaphore is still less than equal to 0 or not. If it is so, that means there are some waiting processes which were blocked because they were waiting for or they needed the semaphore. Okay, so they are put into a queue. So the process in the front of the queue would be removed from the queue and it would be waked up. So that process which was blocked here in the wait operation will be waked up and will resume its operation immediately after this block operation. Okay, so it will start doing again whatever it was supposed to do. So that means after the wait operation, it will actually go directly into the critical section. Okay, so deadlock and starvation, two or more processes, if they're waiting indefinitely for an event that can be caused only by one of the waiting processes, then we say that deadlock occurs. So if there are two or more processes, okay, so let us consider two processes, X and Y. So these are two processes. X is waiting for certain event and Y is also waiting for certain event, and that can be caused, these events can be caused only by one of the waiting processes. If we have only two processes, then X is waiting for one event which can be caused by Y. Y is waiting for another event which can be caused by X. Okay. Okay, so we may have three processes X, Y, Z, where X is waiting for certain event, Y is waiting for certain event, Z is waiting for certain event. And these events can be caused by only one of the waiting processes. So X is waiting for certain event which may be caused by say one of the waiting processes Y. Y is waiting for certain event which can be caused by another waiting process Z. Z is waiting for certain event which can be caused by another waiting process X. So in this case we have circular wait, we say that we have a deadlock. Okay, or we may have say X, Y, Z, three processes. X is waiting for certain event which can be caused by say Y. Y is waiting for certain event which can be caused by say X. And Z is waiting for certain event which can be caused by say Y. So this is also a scenario where we have three processes and each process is waiting for a certain event, and that event can be caused by only by another process which is waiting and which is in the set. Okay, so we'll study exactly where we'll be start when we'll be starting deadlock, what exactly the requirement when deadlock will occur. Okay, say coming back to the discussion of semaphores, so let's say we have two semaphores S and Q. S and Q be two semaphores initialized to 1. S and Q be two semaphores initialized to 1, and the P0 does wait on S, then wait on Q, then say S এর value হচ্ছে 1, Q এর value হচ্ছে 1. So these are the initial values of semaphore S and Q. And also P1 does wait on Q and wait on S, wait on Q and wait on S. And P0 does signal on S, signal on Q, signal on Q, signal on S. This signal operation can be performed in any order, there is no problem. But here in this case, assume that P0 does wait on S successfully. So wait on S, it does successfully, that means this value 1 will become 0. Then before, so P0 does wait on S, but before it can perform wait on Q, context switches to P1. And P1 starts executing. P1 does what? Wait on Q. So this value of semaphore Q, one value will become 0. Alright? And then it performs before, then it tries to perform, say, wait on S, but wait on S, this the semaphore S is already 0, so this process P1 will be stuck here. It won't be able to come out of, so it will be blocked. And when context switches back to process P0, it has already done wait on S, it will try to do wait on Q. And Q semaphore value is already 0. So it will be stuck here in this wait on Q. Okay, this operation cannot be performed. So wait on Q and wait on S. This at these two waits, these two processes would be stuck. Okay, so they both are waiting for certain event. That means P0 is waiting for process P1 to do a signal on Q. When it does a signal on Q, this Q semaphore value will become 1 and it can successfully decrease again. This wait operation will be successful. And P1 is also waiting for P0. P0 would be doing a signal on S. So when this semaphore S value becomes 1, this wait operation would be successful. So P1 is waiting for P0 and P0 is waiting for P1, right? So we have process P0 and P1, two processes are there. P0 is waiting for certain event which can be caused by P1 and P1 is waiting for certain event which can be caused by P0. So in this case, we say that this process, two processes P0 and P1, they are in a deadlock. Then we have starvation, indefinite blocking. A process may never be removed from the semaphore queue in which it is suspended. Okay, so we have already studied this implementation of the semaphore. So we have semaphore corresponding to semaphore S. We would be having one integer value. So it's a structure. So we would be having, say, integer value, and then we'll be having pointer to a list of waiting processes. So we have list of waiting processes in here. Okay, so it is also a linked list. Say we have process P1, process P2, and so on. But this list is implemented in such a manner, so this is not a FIFO, so other strategies are used. So it may so happen that other processes are, when say one process does a signal, other processes are taken out of this queue and they are say waked up, but say process P2 is never waked up. Process P2 is never taken out of this list. Okay, so maybe this list is not a FIFO list. So some strategy is used, but process Q never gets a chance to come out of that. So we say that starvation occurs. Then priority inversion, this problem occurs. Scheduling problem, when low priority process holds a log needed by higher priority process. Okay, and so if we have two processes, say process P0 and process P1, and process P1 has higher priority. Process P1 has higher priority, right? Compared to process P0. P1 requires a semaphore, so it would operate and do wait on S, and P0 also requires the same semaphore. But P0 is a lower priority process, and so assume that P0 has come first and it has already done successfully wait on a semaphore, right? So a low priority process has already acquired a lock, or lock means a semaphore, whereas a high priority process which requires the same lock, that higher priority process has to wait for the lower priority process. So in this case, we say that this is priority inversion. I will discuss this while we'll be discussing real-time scheduling. So this is solved by priority inheritance protocol. So there are some solutions which is known as priority inheritance. Okay, so we'll look into this in detail. We'll try to understand while we'll be studying that real-time operating system characteristic of scheduling in real-time operating system. So before that, for the rest of this lecture, what we'll be discussing is classical problems of synchronization. Classical problems of synchronization. The first one is producer-consumer problem. So in this case, we have a shared pool of n buffers. We have a shared pool which consists of n buffers. N number of buffers are there, and mutex semaphore provides mutually exclusive access. Mutex semaphore provides mutually exclusive access to the buffer and is initialized to 1. And the empty and full semaphore count the number of empty and full buffers. The mutex semaphore provides exclusive access to the buffer. Mutex semaphore provides exclusive access to the buffer. Okay. So what do we have? We have a buffers common buffer area. What we have? We have a common buffer area. We have a common buffer area consisting of n number of slots, small n number of slots we have. And we have producer process and consumer process. Producer process produces item and puts them into one of the free slots in the buffer. And consumer process, when it tries to consume, it will consume one of the item from the already filled up slot in the buffer, right? So mutex semaphore provides exclusive access to the buffer and is initialized to 1. So this producer and consumer process, it might so happen they both may try to access the buffer same time. Like say producer has produced one item and it is ready to put that into the buffer, and the consumer is ready to consume one item. It is ready to, now it is trying to access the common buffer. It's like say we have printer buffer, okay, and they say Microsoft Word, from Microsoft Word we have fired a print job, so that Microsoft Word is trying to access that printer buffer, okay, and at the same time the printer is also ready. It has already received the command of print, so it is trying to access the buffer again. So both the producer and consumer, they are trying to access the buffer same time, at the same time. Or take it, say real life example, say in the canteen, say somebody is preparing say roti or chapati. So that guy is the producer process. So that guy who actually is making roti, so that guy is putting that rotis and chapatis into a common area, and you are actually a consumer. You are trying to get one roti, or say one roti, you are hungry, you're trying to get roti from the buffer area. So it may so happen that person who is actually making roti is accessing, currently putting one roti into the say common buffer area, and you are trying to get a roti from the buffer area. But the problem is such that this buffer can be accessed by only one person at a time, or only either the producer or the consumer. Either that person would be able to put the roti into the buffer, or you'd be able to, if the producer is not accessing the buffer, the consumer would be able to access the buffer. Okay, so that mutually exclusive access to the buffer is that is actually controlled by this mutex semaphore. This mutex semaphore actually provides exclusive access to the buffer and is initialized to 1. So mutex is a semaphore. Name of the semaphore is mutex, short for mutual exclusion. It actually gives mutually exclusive access to the common buffer area and it is initialized to 1. And we have other semaphores as well. We have empty semaphore, which actually indicates number of buffers which are empty initially. Buffer slots, number of slots in the buffer which are empty. So assume that we have 5 number of slots. So initially it would be put into the value 5. Or say we have 3 number of slots. So assume that we have 3 number of slots. Okay. So 1, 2, 3. So 3 number of slots are there. 3 number of slots are there. And full is another semaphore. Full is another semaphore which is initialized to 0. This indicates how many slots are full initially. So these are the 3 semaphores. As you can see, this value is not 1 or 0. So these are counting semaphores. So counting semaphores can assume value more than 1. And mutex is a binary semaphore. It can assume either 1 or 0 value. Okay, so now how it operates, the producer process, when it tries to produce, so it produces one item in its local variable next p. Then it actually, so before it can put the item into buffer, it has to do this thing. So this is the entry section. So in the entry section, and critical section is this part where it is actually accessing the buffer. Okay, so add next p to the buffer. This is the critical section and this is the exit section. In the entry section, this producer process does what? Waits on empty semaphore. What is the current value of empty? This is 3. So this wait operation would be successful and this value 3 would be decremented to 2. Then it does a wait operation on mutex. This value would be decremented to 0. And this add this item that is produced to the buffer. So the producer will put that item into buffer location, the first buffer location. This should be filled up. Okay, then this, it will do what? It will signal mutex. This will become 1 and signal this full, indicating that we have one item in the buffer. Okay, then again, if the producer tries to produce, what will happen? It will make the do a wait on empty. So this would be become 1. Wait on mutex. This will become 0. Add the item to the second spot. So the second spot would be filled up. And then signal on mutex and signal on full, indicating that we have two number of, say, items in the buffer. If the producer tries to produce again, so it will do wait on empty, wait on mutex, then it adds the item into the buffer, third slot is full, and then it does signal on mutex and signal on full, so it becomes 3. Now, at this point of time, so if the producer, so all the buffer slots are full, if the producer tries to produce again, it will do wait on empty. And what is the current value of empty semaphore? This current value of empty semaphore is 0. So the producer process will be stuck here in this wait operation. It cannot produce, or it cannot put the item into the common buffer area, right? So at this point of time, let's see what the consumer can do. So if the consumer comes, consumer will do what? Wait on full. The value of the full semaphore is 3, so wait on full will decrease the value of this semaphore to 2, from 3 to 2. Value of this wait semaphore would be decremented from 3 to 2. Then wait on mutex. Then it will remove an item from the buffer. So one item would be removed. So this would be free. The first slot would be free. And it will do a signal on mutex and signal on empty. Okay, right? So the empty semaphore now becomes 1. At this point of time, if the producer comes and producer tries to produce, it would be able to successfully do a wait operation on this empty semaphore and would be able to put that item into the buffer. All right. Okay. So let's see if the consumer goes on consuming. So consumer again tries to consume wait on full. So this would become 1. Wait on mutex 0. Remove an item. So this item would be removed. So we have 2 free slots. And then signal on mutex, it would be signal and signal on empty. Okay. If the consumer tries to consume again another item, wait on full semaphore, this should become 0. Wait on mutex, this should become 0. remove an item, so one item would be removed from the common buffer area, so all the say slots are now free. Then it will signal on mutex, signal on mutex, say signal on empty, so it will become 3, and it will again try to, if the consumer again tries to consume, let's see what will happen. So we don't have any item in the buffer, consumer tries to consume, so it will do what? It will wait on full semaphore. So now the value of the full semaphore is 0, so it would be stuck here in the wait operation. So when the buffer is empty, if the consumer tries to consume, then the consumer will not be able to consume any item, right? So that synchronization, in this way, we have seen this solution actually using, say, product solution to the producer consumer problem using semaphores actually satisfies those two synchronization requirements. The first was producer should not be able to produce if the buffer is full, and the second was the consumer should not be able to consume if the buffer is empty. So we have seen that this solution achieves those two synchronization requirements. And this is the solution to the producer consumer problem using semaphore. Okay, so now I'll move to the next classical problem, which is this reader's writer's problem, and a solution to the reader's writer's problem using semaphore. Okay, so let's try to understand this problem first. We have readers and writers. Okay, so we have multiple writers, multiple readers. So assume that in a, say, classroom, in a classroom we have a whiteboard. So this is the whiteboard. Okay, and say teachers, they are the writers. Okay, so we have teachers, so they can only write on the whiteboard, so they are actually writers. And we have students here, so students, okay, so we have students, they are actually readers. Okay, so they are actually readers. So we have multiple readers and multiple writers. So normally we don't have multiple teachers in a single class, but it may so happen that while one teacher is teaching, another teacher may come and start writing over the board. So they don't see. So it's unlike in a physical classroom. So the processes, they may be spawned. Say writer process comes and that writer process tries to write into the common area. Okay. So writer processes, they actually writes into the common area, and the reader processes, they actually reads from the common area. Okay. Now what might be the synchronization requirement? The synchronization requirement, if this is the operation of the two types of processes, then the synchronization requirements are that two readers can access, two or more actually, two or more readers can access the shared object simultaneously. Two or more readers can access the shared object simultaneously. Two or more readers. And one writer and some other process cannot access the shared object simultaneously. Okay, so if there are no writers writing, then two or more readers can read from the this whiteboard simultaneously. Okay, the teacher is not writing anything into the whiteboard. So the rule is that while the writer is writing, nobody should be able to access the whiteboard, because while the writer is writing the common area, writing to the common area, that content of the common area is now inconsistent. While when actually the writer finishes writing, then only other writers or other readers can read, or other writers can write, if there are other writers. Okay, so one writer, if one writer is there and some other process cannot access the shared object simultaneously. If one writer is there, then other processes cannot access the shared object simultaneously. Shared data structures, semaphore, mutex, WRT, int, read, count. So these are the shared data structures. Semaphore, mutex, WRT, int, read, count. So these are the shared data structure. Mutex, WRT read count. Okay, so semaphore mutex is one semaphore which gives mutually exclusive access to some read count variable which would be used by the reader processes. And this WRT semaphore actually controls mutually exclusive access to the common buffer area. Okay, so these writer processes, they are very simple. So when a writer process tries to write, what that writer process will do, this writer process will wait for the WRT semaphore, and this WRT, sorry, WRT semaphore, right, is initialized to 1. And this read count is a variable. Read count is a variable, normal integer variable. Okay, it is accessible to all the reader and writer processes. It's not a semaphore. A read count variable, it is initialized to 0, and a mutex is another semaphore which is initialized to 1. So the writer processes, they are coded very simple. So when a writer comes, it will do what? It will first wait for the WRT semaphore. So if the current value, say writer 1 comes, writer 1 finds that the current value of the WRT semaphore is 1, so it will decrement it successfully to 0. So writer 1 is currently writing into the common area. When writer 1 is writing into the common area, if writer 2 comes, this writer 2 will not be able to write because this writer 2 will do a wait operation on the WRT semaphore. And what is the current value of the WRT semaphore? This is 0. Current value of the WRT semaphore is 0. So the second writer cannot write into the common area, so it will be blocked. Okay, and this is true for any further writer if they come. Say if writer 3 comes, and that writer would also be blocked. Okay, only when this first writer comes out of the critical section, that means it finishes its writing job, then this WRT, it will do what? It will do a signal operation on the WRT semaphore, and a signal operation on the WRT semaphore will increase it to 1. Okay, so the first process has finished writing, first writer has finished writing. If we have subsequent writers, any further writers, say W2, so W2 will decrease this to 0. W2 will decrease WRT semaphore to 0. It would be writing right now. Okay, when it comes out of this writing, or when it finishes writing, it will do a signal on WRT, so it will increase it to 1, right? Okay, so this is very simple, but say when say W3 tries to enter into the critical section, or say it is trying to write, so it will decrease it to 0. The W3 is currently writing. So assume that W3 is currently writing. And at this point of time, say some reader comes, say reader R1 comes. So what it will do? It will do a wait on mutex of semaphore. So this is done. So this 1 would be decremented to 0. Then it will increase the read count variable to 1, indicating that we have currently one number of readers. Then it will check whether the read count variable value is 1 or not. So that means it will check whether this is the first reader or not. So if it is the first reader, then it will do wait on WRT. So it would be waiting for WRT. Wait on WRT. So while one writer is writing, this first reader that comes, that reader would be stuck here in this wait on WRT because the WRT semaphore value is 0. So if another reader comes, say R2 comes, R2 will do what? Wait on mutex. So this mutex semaphore value is 0. So this reader R2 would be stuck here in wait on mutex. Okay, and further readers, if R1, R2, R3, say if R3 comes, R3 will also be stuck here in this wait on mutex. So let us see when say this, so that synchronization requirement is satisfied. While one writer is writing, other readers are not allowed to read. So when W3 actually finishes writing, when W3 finishes writing, it will do what? It will signal on WRT. So this value will become 1. It will signal on WRT. Okay, so it will signal on WRT. This value will become 1 and it has finished writing. So at this point of time, if context switches to R1, R1 was waiting on WRT. So it will do what? It will do successfully this wait operation on WRT. So it will decrease the WRT semaphore to 0 and it will execute the next statement. What is that? Signal on mutex. It will be 1 right now. And this process is reading. R1 is reading right now. When R1 is reading, say if R2 is scheduled, R2 was stuck where wait on mutex. What is the current value of mutex semaphore? This is 1. So R2 will be able to successfully do this wait operation on mutex Singapore. So this now will become 0 and R2 will do what? Increase the read count value to 2 and then we will check if read count is 1. No, this is not 1. So this is 2. So it will not perform wait on WRT. It will just signal mutex and it will be reading. So R2 would be reading. Okay, so at this point of time, if another reader R3 comes, R3 will do what? Will do a mutex, so we'll do a wait operation on mutex. So this would be decremented to 0. Read count would be incremented to 3. And if read count equal to 1, no, so it will signal mutex and it would be reading. So R3 is reading right now. So at present, 3 readers are reading R1, R2, and R3. So these 3 readers are reading presently. Okay, so simultaneously multiple readers can read. So any number of readers can read. So at this point of time, when multiple readers are reading, if one of the writer comes, if any writer comes, say assume that W1 comes again. W1 do what? Wait on WRT. What is the current value of this WRT semaphore? This is 0. So this W1 will be stuck here in wait on WRT. It cannot write. It will be stuck here. Okay. So when at least one reader is there, no other writer should be able to write. Right. When this writer would be able to write? When all the reader finishes. Let's see what happens. So when say assume that R1 came first, then R2, then R3. Say R1 is the first one to come out of this critical section. That means R1 finishes reading. So it will do what? Wait on mutex. Wait on mutex. Wait on mutex. So this should be 0. Then it will decrease the read count value. So it will be decremented to 2. Then it will check if the read count value is 0 or not. Yes, so it is not 0. So it will signal on WRT. So it will, sorry, if read count is 0, read count is not 0. So it will not perform this one. It will signal mutex on. Right? So W1, R1 has finished writing. Then if R2 comes, R2 finishes writing. R2 will do what? This part. Wait on mutex. This should be 0. Then read count minus minus, this value becomes 1. If is the read count 0? No. It will towards signal on WRT. Sorry, it's not 0, so it will not perform this one. It will perform only signal on mutex. Right? And R2 finishes reading. Then R3 finishes reading. So what it will do? It will do wait on mutex. Read count minus minus. Is the read count 0? Now it is 0. Yes. So it will do a signal on WRT. So this will become 1. Then it will signal on mutex. So now this WRT semaphore has become 1. So R3 has finished. And if there is no other reader processes, and at this point of time, say this writer W1 is scheduled, then W1 would be able to successfully decrease this to 0 and would be able to write. So W1 is presently writing. Okay, so this is how the synchronization between readers and writer processes they can be achieved using semaphores. Okay, so I'll show you a little demonstration on this. Okay, so say we have reader processes, writer processes. So I'll show you the code later on. Say we have a reader. Say first one a writer process comes. Writer, I have to invoke that writer process with its own ID. Say writer one and how much time it will use. Say writer one will be using say 30 seconds to write. So writer one is trying to write. It's the current value of this. I have to run this. Right. So the semaphores have been initialized by this master program. This writer one is writing for 30 seconds. At this point of time, if I invoke the writer program, so writer 2 comes and it tries to write for 10, it cannot. Writer 2 is trying to write, but it cannot. Only when writer 1 will come out after 30 seconds, this writer 2 would be, is, say, writer 1 finished writing and writer 2 is presently writing. Now, again, say writer 1 comes, it tries to write. Only when writer 2 finishes, writer 1 is able to write. So again, writer 2 tries to write, it is not able. Only when writer 1 will be finishing, then writer 2 will be able to write. So watch carefully. When it finishes, this starts. Writer 1 finished, writer 2 is presently writing, and it will be writing for 10 seconds and eventually it will finish. Okay, writer 2 finished reading, writing. Okay, so these were the synchronizations between writers, among writers. Let's see if, say, one reader, reader 1 tries to read it for 20 seconds. Reader 1 is trying to read, reader 1 is reading. At this point of time, when one reader is reading, if writer comes, writer is waiting. Writer is not able to write. Only when reader 1 finishes after 20 seconds, writer 1 would be able to do that. So watch carefully. Writer 1 has exited, reader 1 has exited, and writer 1 is presently writing. And these readers are in a loop, so it is again trying to read, but it won't be able to because one writer is writing. Now, only when writer 1 finishes, reader 1 is able to read now. Okay, so if I have multiple readers, say reader, and again say reader 2, which is trying to read for 20. Reader 2 is able to read. So we have two readers, reader 1 and reader 2, they are simultaneously able to read. Reader 1 has exited and reader 1 is able to read again now. Okay, so both readers are there, reader 2 and reader 1. And at this point of time, if writer comes, writer won't be able to, because reader 2 is reading, Reader 1 is also reading. Okay, so both this reader 1 and reader 2, they are actually getting access to that semaphore continuously. And once they exit, they again actually are able to enter into the reading again. So because this program has been written in such a manner that readers are in a continuously in a loop, but this writer is not getting a chance. So I just press a Control C over here to close the reader and close this reader as well. Okay. So if I reinitialize this semaphores, then again so this writer 1 is able to write. So there are no other readers, only writer 1 is writing. So it would be writing for 30 seconds, then it would be coming out. Okay, so I can share these codes with you. You can actually run at your home in your own machine. So this is how they look like, the codes actually. This is the code for reader. So this is a simple C program. We have arguments first from the command line. We have say two command line arguments. One is the ID of the reader and the amount of time, the time pointer for which it wants to write. So this lock and unlock. These are the two say library functions. And these are there in some header files, sema.h and sh1. These are not system defined header files. These are written by so some other library functions, not system library functions, user defined library functions. Okay. So this reader process, it looks like this: lock the mutex semaphore, then read count, increase it, then get the read count value, then check it. If it is 1, then lock the WRT semaphore. Lock means wait operation. Then unlock the signal, the mutex semaphore. Then you are in the critical section. Then once you come out, you lock the mutex semaphore and then read count. You read the value of the read count variable, then decrement it, and then you check whether the value has become 0 or not. If it is so, then you unlock the WRT. This is the code for the reader, and the code for the writer is very simple. Before entering into the writing area, so it returns to log the WRT semaphore. Once it is able to do that, it will write into the common area, and then once it comes out, it will unlock the WRT semaphore. Okay, so this is the code for the writer process, and this is the code for the reader process. And then you have another master process which is run initially to initialize the different semaphores and the read count variable. Okay, the semaphore um, WRT is initialized to 1 and mutex is initialized to 1, and this read count variable is initialized to 0. Okay, and you can use this sort of say features which are available. So you can write your own programs for having solutions to the other problems of synchronization, classical problems like say producer consumer, and the next one that we are going to study, which is the uh, dining philosophers problem. Okay, so I shall share this code with you. You can run it on your own machine. So if you have GCC, or any other C compiler which is POSIX compliant, which supports these library functions. Okay. Uh, the last one is this dining philosopher's problem. We have now consider that we have say five number of philosophers. So it is five. It can be so five philosophers who spend their lives thinking and eating. So we have five philosophers who spend their lives thinking and eating. So five philosophers are there. One, two, three, four, five. So they spend their lives thinking and eating. Thinking and eating. Philosophers share a common circular table surrounded by five chairs. They share a common circular table. So this is the common circular table surrounded by five chairs. The table is laid with five single chopsticks. Five single chopsticks are there. And at the center of the table is a bowl of rice. We have a bowl of rice at the center of the table. When a philosopher thinks, he doesn't interact with others. So these philosophers, when they think, they doesn't interact. So they think independently. But when a philosopher becomes hungry, that philosopher can eat depending on whether other philosophers are already eating or they are trying to eat or not. As because there are five chopsticks only, and in order to eat, any philosopher, that philosopher has to pick up both chopsticks, left and right. Chopstick and its left and right. So no other chopstick. So this philosopher cannot stand up and pick up this one. So this philosopher can pick up chopstick, this one left and right. So we mark this philosopher. So this is 0th, 1th, 3, 4. Philosopher 0, philosopher 1, philosopher 2, philosopher 3, and philosopher 4. Then we have chopstick 0, chopstick 1, chopstick 2, chopstick 3, chopstick 4. And these are the different chopsticks. Then philosopher 0, in order to eat, it has to pick up chopstick 0 and chopstick 1. Okay. Philosopher 0 must pick up chopstick 0 and chopstick 1. Philosopher 1 must pick up chopstick 1 and chopstick 2. Okay. So and if say P0 and P1 becomes hungry simultaneously, either P0 and P1 so can be able to eat because they both require C1, right? So P0 left chopstick is C0 and right is C1. For P1 left chopstick is C1, right is C2. So this P0 can pick up C1, C0 then C1, and if P1 tries to pick up C1, it cannot. Okay, so we assume that they actually try to pick up, these philosophers try to pick up the chopsticks in order. First left one and then right. The philosopher can pick up only one chopstick at a time. And when the philosopher finishes eating, she puts down both of her chopstick and starts thinking again. Okay, so this is the synchronization problem. So we have to solve it using semaphore. So we have a semaphore array, chopsticks. Chopstick is the semaphore name of the array, and we have five number of elements in that array. We have five number of elements in the array. So first, what we do, wait on chopstick. So this is the code for philosopher I. So philosopher 0 will wait for this chopstick 0 and chopstick 1. That means chopstick 0. So philosopher I will wait for chopstick I and chopstick I plus 1. So And this all these chopstick elements or the semaphore elements in this array, they are initialized to 1. So if this is the chopstick semaphore array, so we'll be having 5 elements within 1, 2, 3, 4, 5, 1, 1, 1, 1, 1. So they would be initialized to all ones. Wait on chopstick I. So ith philosopher. So if P0 becomes hungry first, P0 becomes hungry first, it will wait for chopstick 1. So it will decrease this to 0. Then wait for chopstick I plus 1 modulo 5. This would be 0 plus 1 modulo 5. That means 1 modulo 5. This is 1. So it will be decremented to 0. Okay, so both of them will be decremented. Then it would eat. So philosopher 0 will eat. While philosopher 1 is eating, if philosopher 0 is eating, if philosopher 1 comes, it will do what? It will try to pick up, say, chopsticks 1. So, but chopstick 1, its value is already 0, so the philosopher 1 would not be able to eat. So, at this point of time, if philosopher 2 becomes hungry, so it cannot. So, philosopher 2 becomes hungry, it will do what? Wait on chopstick 2. It will successfully decrease. Then wait on chopstick 3, successfully decrease. And these two, and philosopher P2 would be able to eat right now. So, philosopher P0 and philosopher P2 is currently eating. At this point of time, if any other philosopher becomes hungry, say P3, P4, P3 cannot, P4 also cannot, before P4 requires C4 and C0. C0 has already been picked up by P0. Okay, so only when P0 finishes, then C actually releases these two chopsticks, C0, so signal on C0, so this should become 1, and signal on C1, so this should become 1. So both these will become 1. At this point of time, if say either C4, philosopher 4 wants to eat, so that philosopher 4 would be able to eat. C4, C0 will become 0. Or if P1 wants to eat, P1 won't be because C1 is available but C2 is not available. Okay, so this way we actually um, control the synchronization requirement or implement the synchronization requirement that should be there among the different philosopher processes. All right. But this solution actually leads to a deadlock situation. What happens if all the philosophers they become hungry simultaneously? So this is the chopstick array, all the elements 1, 2, 3, 4, 5, 1, 1, 1, 1, 1. So all these elements are 1 right now. If at this point of time all the philosophers they simultaneously become hungry. So philosopher 0 picks up its left chopstick, so this becomes 0. But before philosopher 0 can pick up the right chopstick, philosopher 1 becomes hungry and it picks up its left. Before philosopher 1 can pick up right chopstick, philosopher 2 becomes hungry and picks up its left, and so on. So all the philosophers they pick up their left chopsticks and the right chopsticks they are not able to pick up because it has been picked up by the other philosopher or the neighboring philosopher as its left chopstick. Okay, so at this point of time all the philosophers they have picked up their left chopstick, respective left chopstick, but waiting for the right chopstick which can only be released by its right neighbor. Okay, and we say that this is deadlock. The solution to the dining philosopher problem is not deadlock free. Okay, so in this case, deadlock happens. So when all the philosophers become hungry simultaneously, and they pick up their left chopstick, but fail to get the right chopstick, right? So deadlock handling allow at most four philosophers to be sitting simultaneously at the table. Allow a philosopher to pick up the forks only if both are available. That means if both the chopsticks are available before picking up, check whether both the chopsticks are available. If both are available, then only allow the philosopher to pick up. Otherwise, don't. Okay. So picking must be done in a critical section. Okay. So if you pick up, you'd be picking up both the chopstick. Otherwise, you won't be picking up any of the chopsticks. So this must be done in a critical section, and it should be atomic one. That means You should either be able to pick up both the chopsticks, or you should not be able to get any of the chopsticks, right? Or use an asymmetric solution, and odd numbered philosopher picks up first the left chopstick and the right chopstick. Even numbered philosopher picks up the first and right chopstick and then a left chopstick. So odd numbered philosopher, they should pick up first the left chopstick, then the right, and even numbered philosopher, they pick up first the right chopstick and then left chopstick. So in this sort of solutions are there for preventing deadlock in the solution to the dining philosopher's problem. Right? So if you have any question, you can ask me right now. Okay? এটা আমার সিনক্রোনাইজেশন থেকে যা যা বলার ছিল সেটা শেষ হয়ে গেল। তোমরা প্রশ্ন থাকলে বলতে পারো। হ্যাঁ, শুনতে পেলাম না। হ্যাঁ, এই যে রিড কাউন্ট প্লাস প্লাস বা রিড কাউন্ট মাইনাস মাইনাসের আগে ওয়েট কেন দিচ্ছে? হ্যাঁ, এখানে রিডার তো কি বলেছি, সাইমালটেনিয়াসলি মাল্টিপল রিডার থাকতে পারে, তো সাইমালটেনিয়াসলি মাল্টিপল রিডার থাকতে পারে, আর এই রিড কাউন্ট ভেরিয়েবলটা ওই রিডাররাই অ্যাক্সেস করছে। ওকে, তো যখন আমি চাইছি যে যখন কোনো রিডার রিড কাউন্ট ভেরিয়েবলটাকে মডিফাই করছে, তখন সে যেন মিউচুয়ালি এক্সক্লুসিভলি করে। মানে আগে আমরা প্রথমেই দেখেছিলাম একটা প্রবলেম এসেছিল না, যেখানে ওই তোমার প্রডিউসার কনজিউমার প্রবলেমে তোমার ওই কাউন্ট বলে একটা ভেরিয়েবল ছিল, যেটা আইটেম কাউন্ট, যেটা both the producer and the right consumer, the producer প্লাস প্লাস করছে, কনজিউমার মাইনাস মাইনাস করছে। তো এখানেও হতে পারে যে কখনো কোনো রিডার R1 সে হয়তো তোমার রিড কাউন্ট প্লাস প্লাস করছে, আর সেই সময় হয়তো অন্য কোনো রিডার R3 সে হয়তো জাস্ট রিড করে বেরিয়ে আসছে, সে হয়তো তোমার রিড কাউন্ট মাইনাস মাইনাস করছে। তাহলে একজন প্লাস প্লাস করছে, একজন মাইনাস মাইনাস করছে, তাহলে কিন্তু রেস কন্ডিশন হতে পারে, তাহলে আলটিমেট রেজাল্টটা কিন্তু ইনকনসিস্টেন্ট আসতে পারে। তাই জন্য যখনই এই শেয়ার্ড ভেরিয়েবল রিড কাউন্ট ব্যবহৃত হচ্ছে এবং কেউ একজন সেটাকে মডিফাই করছে, অন্যজনও মডিফাই করছে, তখন সেই অ্যাক্সেসটাকে আমাকে মিউচুয়ালি এক্সক্লুসিভ করতে হবে। সেইটার জন্যই এই মিউটেক্স সিমাফোরটা ব্যবহার করা আছে। So this mutex semaphore is used to give mutually exclusive access to the read count variable among the readers. বোঝা গেল রণদীপ? হ্যাঁ, হ্যাঁ, প্রবলেম হতো, কেউ একজন রিডার হয়তো রিড কাউন্ট প্লাস প্লাস করছে, সেই সময় আর একজন হয়তো রিড কাউন্ট মাইনাস মাইনাস করছে। তো এইটা করলে কি সমস্যা হয় সেটা আমরা একবার প্রথমেই দেখেছি। হ্যাঁ, হ্যাঁ, কোডটা আমি শেয়ার করে দেবো। আচ্ছা, এরপরে আমার আছে, এরপরে ডেডলক নিয়ে কিছু বলবো, তো আজকে আর পারবো না। ডেডলক, আর তারপরে রিয়েল টাইম সিস্টেমের শিডিউলিং এর কিছু ব্যাপার দেখবো, তারপরে ডিস্ট্রিবিউটেড সিস্টেমে ঢুকে যাবো। তো আজকে আমি একটু ক্লোজ করছি, হ্যাঁ? থ্যাংক ইউ।
Thank you. Thank you, sir.